Here are the solutions for calculus homework number 14 from the textbook. So, first we have 4 graphs, and we want to decide whether or not the graph is concave up, concave down, or neither. So, just looking at these graphs, concave up would be when we form the shape of a U facing upward. So that would look something like this. While concave down, you have something that is curved downward. And then the only situation that we've seen so far where you have no concavity is if it is a straight line. So just taking a look at these problems, number 1 you can see actually curves off and to the right. If I were to continue this, it would definitely be curving downward. So this is concave down. Number 2, you can actually see a slight curve upward. This is concave up. Number 3, again, you see some kind of slight curve upward, right? Similar to what we saw in number 2. So this is concave up. And number 4 looks to be a straight line. So this is neither. Neither concave up nor concave down. Number 9. So looking at this table, we have values of a function w equals f of t. Is this function increasing or decreasing? And then is it concave up or concave down? So we can actually just take a close look at this table rather than doing a lot of calculations in order to figure out if it's increasing or decreasing. So as time goes on, I see that the value for w decreases over time. So this is very obviously decreasing. So we'll say w as a function of time is decreasing. Now, to determine whether or not it is concave up or concave down, we actually need to look a little bit closer. So I'm actually going to look at this from one instance to the next. I'm going to look at the change in w from one instance to the next. So the first change in w is 100 down to 58. And so that change is negative 42 in 4 seconds. So that's negative 42 in 4 seconds. All right, compare this to the next set, which would be from 58 down to 32, which is negative 26 in the next 4 seconds. Then compare this to the next part, which would be negative 12 in the next 4 seconds. And then negative 4, negative 2, negative 1. So you can actually see that the rate for which w of t is decreasing is itself decreasing, right? So what would this look like if we sketch this plot really quickly? Well, it would look something like this. So that means that our graph is concave up, right? Because our slope is actually becoming closer to 0 over time. So that's what this looks like in a graph. Now, moving on to number 10. For which pairs of consecutive points is the function increasing in concave up, increasing concave down, decreasing concave up, and decreasing concave down? Well, let's just look at consecutive points, and then we'll just label them. So I'll have a column for A. Actually, we'll do this as a column for lowercase a column for lowercase b, a column for lowercase c, and a column for lowercase d. So we're looking at consecutive points. So from A to B, I see that my function is increasing. However, it is curving downward, right? We can see this U shape that it's making facing downward. So it is increasing and concave down from A to B. So increasing and concave down would be right here. So A to B is increasing concave down. From B to C, so my downward facing U curve continues for this, and I'll zoom in a little so we can see this better. And that would mean that my function is decreasing for this little section while being concave down. So that would be D. So from B to C, I'm decreasing and concave down. From C to D, however, I am decreasing, but now I am curving upward slightly as I get to D. So I'm decreasing, but I am concave up. Then from D to E, I'm increasing concave up. So that goes in column A. From E to F, I'm increasing, but now I'm concave down. You can see this kind of flipped over to curve downward. So from E to F, I'm increasing concave down. From F to G, it's not very easy to see, but I can very safely assume that this U shape continues similar to how it did on the left-hand side of the graph. So I'm decreasing concave down from F to G. Then from G to H, it looks like it turns around again and starts curving upward. So I'm decreasing, but I'm concave up. And then from H to I, I'm increasing very obviously while curving upward. So I'm increasing concave up from H to I. So for number 11, I want to graph a function which is increasing everywhere and concave up for negative x, but concave down for positive x. So let me sketch out a set of axes. So it's increasing everywhere, so it must constantly be increasing. I've got to constantly be going positive as I go to the right. So I'll say this is f of x, and this axis is x. So it's concave up for negative x and concave down for positive x. So in order to be concave up, I must have something that looks like this while I'm increasing. And then to be concave down for positive x, so right here where x crosses from positive to negative to positive, I need to be concave down, so I need to start curving downward. So something that looks like this. It doesn't necessarily need to cross at the origin. I could cross at any point along the f of x axis. However, it does need to be concave up and increasing on the left side of the f of x axis, and then increasing but concave down for the positive x values. In number 37, a lizard is encouraged to run as fast as possible. This graph here, figure 1.39, shows the distance run in meters as a function of the time in seconds. If the lizard were running faster and faster, what would be the concavity of the graph? Well, faster and faster would mean that my slope, my change in distance over time, would be increasing. So let's jot this down real quick. Faster and faster seems to imply that my slope should be increasing. So what concavity would that be? Well, I would have a higher and higher slope value, so that would be concave up. Right? It would look something like this. Does that match what we see? Not really. I can see that there's a slight curve down here, but it doesn't really match what we see. For part B, we want to estimate the average velocity during this 8-second experiment. So average velocity is just going to be final distance minus initial distance over the total time that it takes. So I can say that's my time interval, t final minus t initial. And so this average velocity is going to be, well, my final distance, which looks to be about, we'll say 2.1 meters, minus, looks to be 0 meters, so we'll just put our units over here, over our 0.8, also minus 0, and that appears to be in seconds. So my average velocity appears to be 2.1 divided by 0.8, which, if we just put this right into a calculator, should not be too hard to get. So that would be 2.1 divided by 0.8, which is 2.625 meters per second. So I'm given different values of functions f, g, and h, and I want to determine which are concave up, which are concave down, or which might be linear. So first I'm going to notice that I have equal time steps. I have 10 seconds per interval. So I'm going to look at differences for each interval. So I'll do delta f, I'll do delta g, and I'll do delta H. I'm just going to look at how these change over time. So for the first 10 seconds, F goes up by 7. For the next, goes up by 6. For the following one, 5. Next one, 4. Then 3. Okay? So what I can get from this is that the rate at which F is increasing, F increases the entire time, is actually decreasing. The rate is decreasing. Therefore, this would be concave down, right? The slope of it is decreasing. So that would look something like this, if this were f of t. All right, for g, for the first 10 seconds, I go up by 3, then by 3 again, then by 3 again, then by 3 again, then by 3 again. So what would this look like? Well, it would just be a straight line, right? I am increasing at a constant rate, so this is linear. Then, for my final h, I increase by 2 for the first 10 seconds, increase by 3, 4, 5, 6. So what would that look like? Well, it would look something like this, which is my h of t. So this would be concave up. And that's all there is to this homework. So, moving on to our final two problems. Experiments suggest that the male maximum heart rate decreases by 9 beats per minute during the first 21 years of their life, and by 26 beats per minute during the first 33 years. So if you model the maximum heart rate as a function of age, you use a function that is increasing or decreasing, and then should that be concave up or concave down? So we only have 2 data points here, so let's say heart rate, or we'll say maximum heart rate, over age. So we have maximum heart rate as a function of age. And during the first 21 years of life, so I don't really know where I start, but for the first 21 years of life, I decrease by about 9 BPM. So I'm going to guess this is around 160 or so as a good maximum heart rate for now. During the first 21 years, so 21 years is quite a while. So let's say this is 21 years. And then roughly to scale during the first 33 years, so maybe another third here, it actually decreases by 26. So literally just plotting these 3 points, I can see a trend that seems to do something like this. Therefore, we want to use a function that is decreasing and concave down. So decreasing and concave down. For 40, a car starts slowly and then speeds up. Eventually the car slows down and stops. I want to graph the distance the car has traveled as a function of time. So we'll start with a big old graph, set of axes, where we have distance as a function of time. So let's see, it starts slowly and then speeds up. So we're starting slowly and we're speeding up, right? So our rate of change of distance is increasing. Then eventually it slows down and stops, right? At this point, my slope is 0 because my distance is no longer changing with respect to time, right? So again, I started slowly and sped up, right? The rate of my distance change was increasing. And eventually I started to slow down, so the rate decreased, and then I stopped.